Hello and welcome to the Chemistry Academy. In this video we're going to be covering chemical formula, which is mostly relevant for National 5 chemistry. The first part of this will be relevant for you guys studying National 4, and if you are doing higher and are just looking for a bit of a refresh on chemical formula, then you can keep watching too. So if we start off with what a chemical formula actually is, so it tells you the type and number ratio of atoms or ions in a chemical substance. So we're all quite familiar with chemical formulas because we do see them now and again. Like most people will know that water's chemical formula is H2O, carbon dioxide is CO2, but we don't always think about what that actually means and how that's even come about. But that is what it means. CO2 means that in a carbon molecule you have one carbon and two oxygens. In a water molecule you have two hydrogens and one oxygen. That's why it's H2O. Okay, so we're going to go through some examples of how we can work out the chemical formula of a substance from firstly using prefixes that are in the name. This is what's more relevant for National 4 chemistry, and then we're going to look at how we can work out the chemical formula where we're not given any prefixes and we just need to use what's called the valency of the atoms. Now the valency is how many bonds a substance can make, and the data booklet can tell us what those valencies are. So if we start with the prefixes, if you're unsure on how you name compounds in the first place, then you may want to check out my video on naming compounds. You'll find that under my National 4 and National 5 chemistry playlists. So when you can see a prefix in the name, so mono, di, tri, tetra, anything like that, that suggests you can work out the chemical formula just by using that prefix. So if we look at the first example, carbon dioxide, I've already mentioned this before, everyone tends to know what carbon dioxide's chemical formula is, and it's CO2. That's because there's no prefix in front of the carbon, which means that there's just one of them, and there's a di in front of the oxygen, which tells us there's two oxygens. What you need to make sure when you're writing chemical formula is that your element letters are nice big capitals and that your numbers are small subscript numbers. Okay? If we go down to this next one, carbon monoxide. Now mon or mono is a prefix, which tells us we can just use prefixes for this formula. There's nothing in front of the carbon, which means there's just one, and the symbol for carbon is C. Monoxide means, again, there's just one oxygen, so we do one big capital O with no number after it. So you can see the difference between carbon dioxide and carbon monoxide is just how many oxygens there are in the substance. If we then go on to this example, boron, trihydride, there's no prefix in front of boron, which means there's only one of them. The symbol for boron is B, big capital B, and then hydride is hydrogen, which is a capital H, and there's three of them because there's a tri in front, so we put the wee 3 after the symbol. Okay, although the prefix comes before the element's name, the number goes after the element symbol in the formula. This next one here, dihydrogen, so our symbol for hydrogen is H. If it's di, that means there's two of them, so we put a little 2 after there. And sulfide, that means there's just sulfur because it ends in ide. There's only two elements, the hydrogen and the sulfur. And the symbol for sulfur is S. Because there's no prefix in front of the sulfide, it means there's only one sulfur, so we don't need any wee numbers afterwards. So here we've got potassium mononitrate. So there's a prefix in this name, which means we can use the prefixes to work out the formula. The symbol for potassium is K, big capital K. You can always check the symbols in your data booklet. And then nitrate ends in 8, which means we'd want to look at page 8 of our data booklet. If we look at page 8, we find that nitrate is NO3, so capital N, capital O, and then a small 3. And because there's only one of them, we just leave it as that. Okay, there's one nitrate, so it's just KNO3. Here we've got magnesium dihydroxide. Now, hydroxide is a tricky one because it doesn't end in 8 or ite, so it makes you think that there's only two elements in it. But hydrox means hydrogen and oxygen together. So hydroxide is one of those ions that kind of breaks the naming rules. Although it is 2 elements plus oxygen, it doesn't end in 8 or 8. It's called hydroxide, and you will find hydroxide on page 8 as well. So magnesium symbol is Mg, capital M, small g. Again, it's important that when it's a capital, you put it as a capital. When it's a small letter, you show it as a small letter. And hydroxide, if we look at page 8, we will find is O, capital H. Because there's 2 of them, and this is a group ion, so group ion is anything you find on page 8, we need to put brackets around it because it's a group, and then we put the 2, small 2, on the outside of the brackets. Okay, and then we've got last example here, calcium dinitrate. So calcium symbol is C, capital C, small a. Nitrate ends in 8, we'd find that on page 8. We would find again that it was NO3, but there's 2 of them, so because again it's a group ion, we put brackets around that and put a small 2 on the outside. Okay, so that's how you do the chemical formula if you're given a prefix. If you're given a prefix, go off of that. However, if you don't get given a prefix, in the case here, hydrogen phosphide, calcium fluoride, sodium sulfate, iron 3 oxide, you can see there's no monos, dis, tris, or anything like that. This is where we then need to use the valency. So this is what then is National 5 level. So this is more National 4 and National 5 level using the prefixes, but the valency is really just National 5 level. So you don't need to continue watching this video if you're doing National 4. So valency is, again, like I said before, just how many bonds the substance can make, and what group in the periodic table the element's in essentially tells you what the valency is. So we get this valency pattern that we observe for the groups. So from group 1 up to group 8 or 0, you get the pattern of, so for group 1 the valency is 1, for group 2 it's 2, for group 3 it's 3, for group 4 it's 4, but then when we get to group 5 the numbers start to drop again. So group 5 only make 3 bonds, group 6 make 2, group 7 make 1, and group 0, or the noble gases, make 0. That's why they're called group 0, because they make 0 bonds. Okay, so it's a good idea sometimes to write this on the top of your data booklet, usually on the electron arrangements page. You just write the valencies 1, 2, 3, 4, 3, 2, 1, 0. Just try and remember that pattern. It links in with what their charges are as ions. So if you're not sure on ions, you can go and watch my video on ions. But anything in group 1 has a single positive charge. Group 2 are 2 positive. Group 3 are 3 positive. Group 4 tend not to form ions, so we don't really have an ionic charge associated for them. But then group 5 become 3 negative, group 6 2 negative, group 7 a single negative, and again the noble gases don't form ions. So the valencies numbers do match the charge numbers on these ions. So if you just try and remember that pattern, 1, 2, 3, 4, 3, 2, 1, 0. When it comes to transition metals, so that big block in the middle of the data booklet in the periodic table, they don't have set valencies. They're quite flexible in how many bonds they can make, so any valency of a transition metal will be shown to you in the name in Roman numerals, just like the silver 1 oxide. So this means that in this compound, the valency of silver is 1. Okay, you could get silver 2 oxide, and that would be silver with the 2 Roman numeral. Okay, so when you have a transition metal in your compound, look to see what the number in the Roman numerals is, and that will tell you the valency. Again, it also relates to the charge, so the silver would be a 1 positive charge in this substance because its valency is 1. So if we have a look at the examples here, we've got hydrogen phosphide. Now, I like to use the SVSDF method, where we've got symbols, valency, swap, divide, formula. So we start off by the symbols. Hydrogen's symbol is H, capital H. Phosphide, or phosphorus, is a P. We then go and look up their valencies. So if you look up the periodic table, you will find hydrogen in group 1, which means its valency is 1, and phosphorus is in group 5, which means its valency is 3. Then the second S is swap, so we swap these over. We put the 3 here and the 1 here. And then the D for divide is to divide by the smallest number, or divide to get the whole number ratio. This is the simplest whole number ratio we can get because we've got a 1, so that means it stays as 3 to 1, which means our formula has 3 hydrogens, because there's a 3 underneath the H column, and then 1 phosphorus, so it'd be H3P. Okay? If we look at this example here, calcium fluoride, so SbSdF. The symbol for calcium is Ca. Fluorine is F. The valency for calcium's in group 2, so its valency would be 2. Fluorine is in group 7, so its valency would be 1. We swap them over, we get 1 and 2. We can't make that any simpler as a whole number ratio, so it stays as 1 and 2, which means we have 1 calcium and 2 fluorines, so it would be CaF2 would be the formula. Sodium sulfate, SbSdF. Sodium symbol is capital N small a. Sulfate you would find on page 8, and you would find it's SO3. And with the group ions, they give you the charge in the formula. They tell you it's a 2-. Now remember I said about the metals, the transition metals, that the valency number is equivalent to the charge. Same with all these. So if the charge is 2 negative, that means it's got a valency of 2. Sodium is in group 1, which means its valency is 1. Swap them over, we get a 2 and a 1. We can't simplify that ratio any further, so it stays as 2 to 1, which means we have 2 sodiums, so Na2, and then 1 sulfate, SO3. We don't tend to write the charge on the chemical formula. You would add that in if you were asked for the ionic formula. For the last example here, iron 3 oxide. Our symbol for iron is Fe. Oxygen symbol is O. The valency of the iron in this compound is 3, as per the Roman numerals. Oxygen is in group 6, so its valency is always 2. If we swap them over, we get 2 and 3. We can't simplify this ratio, because if we were to divide by 2, we would get 1 and 1.5, but we can't have half atoms, so it has to stay as 2 to 3. So that means we've got 2 irons and 3 oxygens. Okay, so a common misconception with the transition metal substances with the Roman numerals is that there would be 3 irons in this compound, but that's the valency. So you need to always double check what the valencies are, do the swap and drop, and then we would see that actually there's 2 ions in this substance and not 3, although the valency is 3. Okay, just to finish off, we are going to talk quickly about ionic formula. So ionic formula is essentially the chemical formula with the ion charges put on. So if you're asked for an ionic formula, just do the SVSDF process to get the chemical formula, and then use your knowledge of ions to add on the ion charges at the end. So if we look at this substance here, oxygen, it's in group 6, and everything in group 6 always has a 2 negative charge as an ion, so we would just put 2 minus up here. It doesn't matter that there's 3 oxygens, because we're just writing the charge for each individual oxygen ion. The iron, because it's a transition metal, its valency is tells us what the charge is. So because the valency is 3, then it means the charge is 3 positive. Okay, metals are always positively charged. So whatever the Roman numeral is, that's the charge number with the positive. So for silver 1 oxide, it would be a 1 positive charge. If it was silver 2 oxide, the silver would have a 2 positive charge. If we then look at the sodium sulfate, sodium's in group 1, so it's always going to have a charge of just single positive. Sulfate, the data booklet tells us its charge is 2 negative, so we put that there. So that's the ionic formula for sodium sulfate. For calcium fluoride, calcium's in group 2, so its charge will always be 2 positive. And then fluorine's in group 7, which means that its charge is always going to be a single negative charge. Okay. This hydrogen phosphide is not an ionic substance, it's covalent, so we wouldn't have any ionic charges there. For the calcium dinitrate, calcium's charge is 2 positive because it's in group 2. So we put a 2 plus up here. The nitrate charge, the data booklet tells us, is in a negative, and the charge has to go in the brackets. So if you have more than one of the group ion, you put brackets around it, and the charge of it goes in the inside of the brackets, but the number of how many of that group goes on the outside. Same with the hydroxide. Hydroxide's got a single negative charge, so that charge would go in the brackets, whereas the number of hydroxides we've got goes on the outside. Okay. Magnesium has got a charge, that's meant to be 2, sorry. Magnesium's got a charge of 2 positive, so that would go there. Okay, so that's how you come up with the ionic formula. You just work out the chemical formula and then add in the ion charges after. So hopefully this helps you with chemical formula. Just remember it's the prefixes that are mostly for National 5 and 4, but then the valency stuff is just National 5 only, as well as the ionic formula bit at the end. So if you find this helpful, please give it a like. Don't forget to subscribe, and I'll see you again soon.